Welcome. I'm Dr. Dave Turner. I'm the application scientist for the Beocat supercomputer at Kansas State University. We also help manage the BeoShock cluster computer at Wichita State University. This is a an overview of some advanced high-performance computing usage that's applicable to both of the cluster computers. I'll be showing some examples on each computer, but basically most of this information applies equally to both systems. Most of the topics I'm covering here are fairly generic, so they would be helpful to most users. I've already posted a video that's an introduction to Beocat or BeoShock, as well as one that's an introduction to the Linux operating system that both use and Bash shell programming. This is more advanced topics, and again, I'll be jumping around a little bit more in this one and covering a variety of topics. The last two here are more specific to people using Python. So if you're not interested in Python, you can definitely skip the last part here. So the first topic I want to cover is interactive jobs. Most of the time on cluster computers like Beocat and BeoShock, we run things through the Slurm job scheduler. So we have our scientific application, and what we do is we submit a job script that tells Slurm what resources we need, like the number of nodes and number of cores and memory and so forth. And then we give a list of the commands that need to be run, including our application. It's sometimes beneficial to run more interactively, especially when you're trying to develop a code or debug a code. And the head nodes are made for that a little bit, but resources are limited there. The head nodes typically have about 8 cores, and there are limits put on how much memory you can use and stuff like that. So there's a couple ways of using Beocat and BeoShock interactively. One is through the web-based on-demand uh, application, and that allows you uh, to get in through the web browser and to use the resources interactively, for example, in a Jupyter notebook or something like that. And that's a good way to develop your code. But you can also work interactively from the command line interface as well by asking Slurm to give you the resources that you want. And that's done using the srun command. Um, so typically you can't SSH into a given node for security reasons. You are allowed to if you already have a job running there. But you shouldn't just SSH in and run applications on a node. So srun actually allocates that space just the same way as you would get if you were submitting a job to it, but it drops you into it interactively instead of actually starting any commands. When you do it, this is an example of the srun command here. You can give it a set of parameters just the same way that you would tell Slurm in a job script what you want. And you don't necessarily need all of these. These are examples of some of the options you can have. The -J allows you to specify a job name. The -N sets the number of nodes. Lowercase n sets the number of cores. So on this, we're asking for 16 cores on one node. The -T allows you to ask for a certain amount of time. asking for memory. This is using a minus minus mem equals. These are the single letter options for asking for these resources. There are double minus sign methods of looking at this as well. But here we're asking for 30 gigabytes. And then you can ask for constraints like on Beocat if you just want a certain family of systems. We have them named so you can ask for the moles, for example. This is the priority. If you want to ask to have your priority, if you on Beocat, if you have priority for a certain set of nodes, that'll be set automatically, so you normally don't need to use this. And then this is just specifying at the end that you want to be dropped in to a bash shell. So let's try this out. And we'll do this on Beocat. I'm just going to name it my job just as something arbitrary. Let's go ahead and do srun test instead. And I'm going to skip the class and the priority because the priority will be picked up automatically for me. So once I do that, the job has to go through the queue, but the queue is very short at the moment, so it put me right on. And it put me in node wizard 23. That's the common one that I get dumped on because that's the one I have priority on as one of the Beocat administrators. We own that node, so we have priority on it. So I'm now on Wizard 23, and I can do whatever I want there. But I'm on there not because I SSH'd in. But if we look with kstat at my jobs, you can see that this is actually a job that's being run. The job name again is srun test. It's on 16 cores there. And you can see I requested 30 gigs. So this is a way of getting into a compute node and having those resources specifically allocated to you. I own these 16 cores now, just the same way as if I submitted a separate job script, but I can run on them interactively. So why would you want to run interactively? Again, this allows you to develop and debug your code maybe a lot easier and with a lot more resources than you could on the head node, for example. So some of the reasons for running an interactive job this way are the same as doing it with on-demand. Okay, so let me get out of this. So array jobs are another advanced feature of Slurm. One thing we see a lot of that we try to get people away from is a lot of times you need to run a lot of similar jobs or maybe the same job on different input parameters or different input files. And so people write scripts to generate the Slurm, generate and submit individual jobs to Slurm that again are going to vary by just a little bit. And I've seen people do, dump 10,000 jobs into Slurm. And then when we look at the queue, we can't tell what other jobs are there, and Slurm can't either. Slurm has a certain depth that it looks into the queue. So if one person dumps 10,000 jobs in there, that maybe need a lot of resources. Let's say they each need a GPU and we only have 170 GPUs. Well, they're going to sit there a long time. But there may be other resources available that someone who submits a job after that uh, could use right away. But if Slurm can only look, 5,000 jobs deep, it's never going to see those other jobs. So dumping lots of similar jobs into the queue is troublesome in many ways, both from us looking and seeing what's there, but also from Slurm being able to manage those jobs. If they're similar, the best alternative is to use an array job. An array job could do the same thing with one job script, uh, but it's essentially the same as managing all those individual similar jobs from a single job script. And what you have to do is add one line to the first part of your job script, like this, that is going to tell Slurm that this is an array job with tasks from 1 to 5, and then the colon is going to provide a step of 2. So if in this case, that one job script would run 3 jobs with the environment variable slurm array task ID set to 1 in the first script. In the first job, it would be set to 3 in the second and 5 in the third because we're stepping by 2 here. If you got rid of that :2, then it will run 5 jobs with the Slurm array task ID set to 1, 2, 3, 4, 5 in the individual jobs. So this is a way of constructing a set of jobs from a single script. Let me show you an actual test here. So again, all that's different here is we added in this one line here that says I'm going to have an array, and this one leaves out the step. The tasks are going to be from 1 to 5. So it's going to run 5 individual jobs with the Slurm task ID set differently in each one. And they're going to be from 1 to 5 in this case. So if we just run this, let's do a S batch of sb.array. Now they've already run because they're very short. So let me see so these 5 jobs here at the end, that's the output from the 5 original jobs. And if we just list the output for all of them, each of them does a host name command. So all of these ran on Wizard 23, but you can see hello from array task ID, and you can see that that's different. So these didn't really do anything with the different array tasks. That's what you as the programmer would have to figure out how to use those different array task IDs in each individual job so that they do something different. So in your job script, you could do a variety of things. Instead of just echoing it out, you could run your application with that as the input, and then each of those applications would have to do something different based on that Slurm array task ID that's being inputted to it. You can also run your app on a different input file. For example, you could have your input files named input.1, input.2, input.3, and then your app would just take those different inputs, for example. You could also have a file that is a list of all the input files or input parameters, and you could do a little tricky programming and say, well, Slurm array task ID 1 is going to take the first one of those. So it's up to you as the programmer to decide how each job uses the different Slurm array task ID. And if you need help with that, uh, please contact the administrators and we can help with the writing of your array job. Now, again, the good thing about array jobs is that they don't clog the queue. When you run, it looks like just a single job when it's sitting in the queue. So Slurm sees it both as a single job from the point of view of listing it there, but it knows that it's multiple jobs, 5 jobs in this case. So it won't hurt you on your priority or how fast your jobs get run in any way. But it helps Slurm in being able to treat it like one job of many similar jobs. And then it also helps us as administrators to be able to look at that. It also helps you in managing that, in that if your array job is sitting in the queue and you need to kill it off, you can just kill off that one job ID and not be dealing with, potentially 1,000 that you'd have to kill off. So we very strongly encourage the use of array jobs as opposed to using a script to submit lots of similar jobs. Okay, so let's move on to some advanced Slurm job debugging help. So KStat is very useful in monitoring your jobs. KStat with a -L provides a longer list, just the same way that LS with a -L gives you a longer list of information. So if I'm on Beocat and looking at just the warlocks, we'll try to find one that's a little interesting here. Okay, let's look at Warlock 14. It's running 16 cores out of 128. What the long list does is it tells you more information, like how much space is available on the local disk. If you're using /temp, this says that there's 1.8 terabytes on the local disk. It also tells you the amount of networking. We typically on Beocat have 40 to 100 gigabits per second, and this will tell you how much of that is being used. We have one user with 2 separate jobs here, and one of the things that's most useful about the -L parameter to KStat is it tells you the CPU utilization here. So these jobs are running with nearly 100% CPU utilization, which is great. That's what we look for. And this is updated once every minute. So I'll cover in a second how to get more dynamic information about this, but this is a good way of getting a snapshot once per minute of how your jobs are running. The other thing that this is good for is giving you the snapshot of how much memory you're using. So this user is using 171 gigabytes currently, and that's also the maximum that they've used. They are using 171 out of the 500 gigs that they allocated. So that's reasonable to use to request 500 gigs. But this is a good way of uh, finding out how much memory your job is using when you're starting to run a new application or a new application with a different size of input, is to just guess at how much memory you need, do a K-stat with the minus L, and find out exactly how much it's using. And then you can, next time you run it with a more reasonable amount of memory. So there's a lot of information that you can get from the minus L command. Um, for nodes with GPUs, it'll also give you information on the GPU usage. Trying to find one here. Let's see. So it will give you information also on what type of GPU you have on that system. So on Dwarf 38, there's two GPUs. They are NVIDIA RTX underscore A4000s. And if you're requesting a specific type of GPU, uh, then that's the string that you would use, is the GPU colon. I think this is probably incorrect. That needs to be, yeah. So uh, you can use kstat minus L to get the string that you would use to request a certain type of GPU. So you'd put in your script a minus minus gres equals GPU, comma, or colon, and then the type, if you want to specify a type, then colon, and then the number of GPUs. Uh, so you can also get GPU utilizations and stuff like that using the minus L. So it just gives you a longer list of information about what's on that node and what each of the jobs is doing on that node. So other things that you can do to get additional information about uh, your job is to SSH into any node that you have a running job on. I actually have, as an administrator, additional privileges so that I can SSH into any of the compute nodes, but you're only allowed to SSH into the ones you have a job running on. Let me try to find a node with a few things running on. And once you get in there, you can request uh, to do a few different things that are very useful. Let's go Wizard 35 there. So that has some jobs running GPU stuff there, is what I'm looking at. And so we'll look at some of those, and I'm noting the name of the person there. So One thing that I can do is the NVIDIA-SMI command gives you a probe into what is running on the NVIDIA cards. So since there's 4 cards in there, they're named 0, 1, 2, and 3. And here's what's actually running on them. Something's running on 2 and a different one's on 3. And the actual job is called NAMD3. That's a classical molecular dynamics code. But you can look at information here about uh, the percentage of time that's being used. So these are both using 99% of the GPU utilization. So that's awesome. And then the memory is there somewhere. Here it is. So it's not using a lot of memory, which is fine. It uses what it needs. But the fact that it's using the GPUs very heavily is awesome. In general, you don't need to run this much because, again, we can do kstat minus L on Wizard 35, and that'll give you a snapshot of what's going on. So in this case, we can see that same information here, where this job is running on GPU 3. It'll tell you what the GPU card is. It's running at 99% utilization, and this is the memory. The more helpful part of getting into a node that you're running on is running HTOP, because remember, this gets updated once per minute, the CPU utilization and the GPU utilization. If you want to look at the GPU or the CPU utilization and what processes or threads are running on each core, you can use the htop command. And I'm going to specify, you can see a lot of this, everything is going to have lots of little threads running by the root and so forth. I'm going to specifically ask by hitting the U to get user, and then I'm going to use the arrow to choose the user that's running stuff on the GPU. And now this tells me exactly what cores they're running on. It's a 4-core job, and their stuff is running on cores 20, 21, 22, and 23. Let's see. Maybe I'm wrong about the number of cores. But this tells you exactly what cores it's running on, and those are mostly these up in this range. And so you can actually watch the utilization as it's updated every second or so. You can also look and see exactly what thread is running on each one, or threads. And that can be very helpful to get a more dynamic listing or view of what is going on each core. So that often gives me a lot of better information on performance issues that might come up in a given application when I'm trying to understand why something is not running as it might otherwise. So I'm going to hit Q to get out of that, and then I'll exit that node. So the other thing, the other suggestion I have is for advanced Slurm debugging is kind of a straightforward one. If you get an error message, the first thing you should do is, quite often the first thing we do is Google the error message or Google the app name followed by the error message. So again, that last app was NAMD3. If we were getting some error message in that, we would do a Google search for NAMD3 space and then the error message. We do have some users around campus who do a good job of Googling the error message first. It's common that you know the app better than we do. Uh, if it's a problem with the app and not the system, for example. But we strongly encourage you to try to solve uh, the error, at least to the point of Googling it first before contacting us. The other thing is, if you do contact us through the ticketing system on Beocat or Beoshock, give us plenty of information. We often get way too generic of emails coming in saying, "Hey, my job doesn't work. Can you help me?" And that doesn't give us anything to to work with. So give us the basic information, like what's the path to your job. Always give the job ID, the job script name, and the exact error message. Also give your KSU EID or WSU ID. That's especially true if you're emailing us from something that doesn't contain those. That happens a lot at Wichita. You might be using your Wichita email that doesn't contain your ID, and we need to know that to get to your home directory. Okay, let's go over some more advanced KStat usage. KStat, again, is very useful for monitoring uh, programs and looking at performance. I've added a lot of things over the last year that allow you to look at a given uh, run or even the entire system in a better way. And so I wanted to go over some of these more recent ads. Um, Anytime you need help, you can always do KStat minus help and get information on how to do these things. So as I add features, I also add to the help. So a lot of what I'm going to cover here is under graphs and tables. So let's start with a table. KStat normally allows you to look at a snapshot of what your current performance is. And to get performance over time, you used to have to look at a web-based app called Ganglia, and going back and forth, I would prefer to do everything and have everything at your fingertips with KStat. So I added in some of the same capabilities of looking at performance over time or memory usage over time and stuff into KStat. So the data is in the database and is collected every minute. You can also specify, I want it in every hour. So I put in the example every 60 minutes here. But let me grab a job that I ran a while back. This is asking for all my jobs in the last 10 days. And this is a job ID that I'm going to look at. So if I do a KStat minus table, let's look at the CPU first. And we want to just do 60-minute averages. So one line per hour. And I put the job ID in there. And what I'm going to get is a list of the usages over time for every 60 minutes. So for the first part, what we're seeing here is usage that's less than 100%. And that's just why this application is concerning, is the usage is somewhere between 60 and about 76% there. And so it's not the 100% or close that we would have wanted. And that's showing up as idle time here. So if it was disk weight, then we'd blame the parallel file server as slowing things down. And I would talk to Nathan about whether he was doing some rearranging of data that might have affected it or something like that. But it's doing some idle stuff, and we need to address that. But by looking at this over time, uh, it allows us to see that the usage was slower at the beginning and then it settled down. We can also look at the GPU usage here. And all I'm going to change is the G there. So we're going to look at the GPU utilization. And you can see the total memory used stays pretty consistent. Now, the GPU utilization is fairly low in this case. It definitely speeds up the program so that the users want to continue using it. But this is something that we should look into further because uh, uh, we would like to get more use out of those high-end GPUs. They are offloading work from the CPUs, which is good, but we want to get more utilization out of it. So these are some examples of how you can look at a table and how it can give you information about how things change over time. The memory usage as well can be interesting in that some jobs, if you have a memory leak where you're allocating job or allocating memory each step, but not cleaning it up, that would show as growing memory over time and things like that. You can also see here that it hit some disk swap, just a little bit of disk swap over time, so I'm not worried about that. So the tables are useful for seeing performance over time. We can get graphs of this as well. Cluster computers aren't really meant to do graphics, but you can create a pipeline, an X11 pipeline when you log in that allows you to that allows KStat to display a graph on your system. So on my Apple, I have to have Xquartz, which is pretty commonly available, to be able to display a graph. I'm not sure what it is on a Windows system, for example, but chances are that your system is set up so that it can display things just fine. So the main thing we have to worry about is being able to create an X11 tunnel, essentially. And that's pretty easy. This example is for getting into Bioshock at Wichita. All you have to do is add this minus capital X, and that opens up the connection for X11 so that information on the graphics can be piped back to your local system. So you just do your SSH with the minus capital X is all you really have to add in there. You can set up these connections in your .ssh/config file as well. And if you're doing that, you just have to add an additional line forward X11 space yes to your config file. So if you don't want to do that, you can do these same graphs, and when you run KStat, it just won't display them right away. It'll put the file in the same place on your home directory in a file called .kstat.gnuplot.png. The PNG is a type of image file. So you can run the same thing, and then you can just manually move this and rename it and move it to your local system and display it. So if we want to try that here, so we're going to use all the data, so we don't need to do a 60-minute average. So that's all you need to change is put graph instead of table. And then again, you can still do just a 60-minute average, but we're just going to go ahead and use the all the data so that it's going to have one uh, basically one data point for each minute. And since this is displaying back to uh, sometimes the X11 connection gets a little messed up. I forgot to specify usage. Sometimes the user gets messed up. So there it says that it plotted things to the PNG file, and now it's starting to display it. So again, you can see that the usage here in green, the user part, the good part, was less than 100% at the beginning, and then it kicked in and was mostly good for the rest of the run. Uh, the red is the idle time, so that's the exact opposite in this case of the user time, the good part. And the IO wait and the system time are down here, they're 0. So we can't see that. But seeing things graphically is very helpful at times. I think the table usage is good enough most of the time, but you can certainly generate graphs. And I am updating the way graphs are held right now, since there's a lot of interactivity with the ability to use the menus up here. It's a little more than is needed to just generate a graph. So anytime I move the mouse pointer, it has to update. So I am fixing some of that at the moment. So let's get rid of that. Here's just some more examples of uh, graphs of utilization. This shows GPU utilization at about 35% for the most part, but you see occasional dropouts. This is, again, just more dropouts in this area are what you're seeing. This is CPU memory here, a graph. And here's a case where you can see that the memory is increasing and then it's getting cleaned up, increasing, then cleaned up. But overall, it is gaining here. So that might be fine, but it might be an indication also that that some of the memory is not being cleaned up, uh, and that's referred to as a memory leak. So one of the things that we look at more as the administrators are what the total usage is on the cluster. And so this is information that we might be asked for by the directors, by Dan Andreessen on Beocat and Terence Figge on BeoShock, for example. They might want to know what the usage is over time. And this is a table generated for all the nodes. You can ask for a specific node if you want to look at a specific node. This is for all of the nodes here. And let me just run that on BeoShock. Now, this is going to take a few minutes on BeoShock, but to tabulate all the data, the first thing that's nice is it tells you how many nodes there currently are, how many cores, how many GPUs, and what the total memory is. So if we do the same thing on BeoShock, it's a smaller system. So it comes back a lot more quickly there. So 21 nodes, 768 cores, 8 GPUs, 7 terabytes of memory. And what we're doing is each day is listed here as a line. How many cores are used is one of the common things we want to look at. The load is also here. This is the memory used, allocated, and total as well. So you can see down here, a fair amount of the memory was actually being allocated and used. And 294, here's we're up to 466 out of the 768 cores. And you can see over the days, let me, that here we got close to the 768. Oops. Sorry, this is the core usage. So we're getting pretty close here to the full usage there. And so you can just see the usage over time here of the entire cluster. So here we had 703 cores out of 768 used, and then a few days later, only 112. So it does bounce around a lot. So Bale shock, the data came back. Again, we have 360 days total since I started keeping track of in this database. So 304 nodes, 688 cores, 172 GPUs in the database, and about 55 terabytes on Beocat. So you can see here, very few cores are being used. So we may have been doing maintenance or something at that time. But at times 3,000 cores, a lot of bouncing up and down. Right now, we're only using maybe a quarter of the cores. It's beginning of summer, so it may be kind of a time when people are traveling a little bit more. But this is a useful way of looking at the entire cluster over time or a given node over time. Okay, advanced file access. And this will be a little different on Beocat and Beoshock. On Beocat, each user has 1 terabyte of memory on their home directories. That's the amount that you can use in /homes. If you exceed that terabyte, then your home directory is not going to be backed up. It is triply redundant storage, so 3 specific hard disks would have to fail to lose any data, which is very unlikely. But not backed up means that if you remove something that you didn't want to remove, it means we might be able to back it up or might be able to recover it from a backup as long as it wasn't something that you generated in the current day. So the backups are done nightly. So it's good to keep less than a terabyte on your home directory. If you exceed the terabyte, you get up to 2 terabytes before there's a hard limit, and you just wouldn't be able to use Beocat until you delete some of those files. On Beoshock, there aren't the hard limits at the moment, but there's also, we have a full petabyte on Beocat. There isn't as much on Beoshock. So if you're going to use more than a terabyte, you should really contact Terrence Figge and get approval for that because it is a more limited resource. On Beocat, if you need more than your 1 terabyte, You can actually purchase or rent space. Uh, Instead of slash homes, you would be given a slash bulk uh, directory, and you or your advisor would pay $45 per terabyte per year for that, and that's billed monthly. There's also scratch space available on Beocat. Uh, there's 270 terabytes, but this is meant for short term. So if you need to deal with a very large data set, you can download the data set, put it on Fast Scratch. You simply create your own subdirectory there, and then use it and then delete it. Uh, the space is purged monthly, so if you have any files there that have a most recently updated date of that's more than a month old, they will get purged. This is a shared resource, so keep that in mind as well. While homes and bulk are parallel file servers using the Ceph parallel file uh, system, there can be issues with file locks there, where if your code or codes are opening up lots of files on the same uh, directory and writing to those at the same time, because it's a parallel file server, uh, each time one is opened, that can lock that directory so that you can't access the other ones for writing. If this happens, it's normally you would be coming to us and saying, hey, I'm not getting the performance I expect. What's the deal? And this is one of the things that we as the administrators might spot and say that, oh, that's a problem with the parallel file server. Let's just move you over to running on Fast Scratch. It's a different file system called ZFS. It's very fast, but it doesn't suffer from the file lock systems. So in that case, you just create, again, a directory on slash fast scratch. And at the beginning of your job script, you just move your input files and your code files over there, CD to there, and run it from there. Okay, file sharing using ACLs. ACL is an access control list. It used to be that file sharing was easier in that you just used the chmod and changed your group access for a subdirectory so that you would enable other people in your priority group uh, to be able to access that subdirectory. But uh, it's a little better security to use an access control list because you can specify sharing to a group or to an individual. Uh, it's a little more sophisticated or complex as well. So what I've done is I've written a script called set ACLs that can help you in doing this. It does this automatically for you, but it also, as it's doing it, it tells you the manual commands that you would have to have done in order to do this yourself. I very strongly recommend using the set ACL script rather than doing it manually. So you can always do set ACLs minus H, and it gives you the command that you need to, command options that you need to do right up front, as well as an example here. And that's basically what we're going through here. If you have, I'm going to create a directory, and then I'm going to do uh, set ACLs. I'm going to give read permission, and I'll give write permission as well to the group KSU. So this is the priority group that includes all the administrators. Now, if I want to give access to a particular person, then I specify that person's username there. And then I specify the full path to the name, to the directory that I want to share. Now, as we do this, it says exactly the commands here. These are set FACL commands that it's doing. And so it's here setting the group. This is the user, but it's got to open up the home directory first and every directory leading up to it. That's one of the complicated parts about it. And not only do you want to set these priorities, but you want to set the default. The -D here sets the defaults as well. So that's kind of the tricky part is here we're opening up the home directory with the -X to each. And then for this particular directory, we're opening it up recursively and then setting the defaults so that if that user or a member of that group is in there and creates a file, that it'll also be accessible by the people that we want it to. So you would have to do these 6 commands rather than just doing the one set ACLs command if you wanted to do the same thing. And then the last thing that the script does is it does this get FACL command on that directory to show what the results are. And so the results are that I have access because I'm the user, but I gave usage access as both read and write to the individual Moses and to the group of administrators. So everyone in the group, KSU, CIS, HPC. So, and I gave again, read and write. So now anything So now anything that's created in there should have the same access rights as well. So that if the user Moses came along and put something in there, then Moses and everyone from that group, as well as me, should all have the equal rights there. So again, I very, very, very highly recommend doing this using the setACL script that I wrote up rather than doing it the manual way. But this is the best way to share files now with other users. Okay, so the last thing I want to do is go over kind of briefly creating a Python virtual environment, and this is in our documentation. So I'm going to go over it a little quickly. And this is the last 2 slides. So if you are not interested in Python, you can kind of skip it out on the remainder here. So the first thing is, why do we need a virtual environment for Python? You can, if you're on your own desktop or laptop machine and running Python, you can do your pip install and install certain packages, and they get installed on the entire system. And you can't do that if you're on Beocat or Beoshock, because we don't want you to install something for other people. It's not even good to install things in one place for Python, because different applications may need different versions of the same package. They don't always play nice together. So for each project, it's a good idea to create a separate virtual environment. The first thing you need to do is choose which version of Python you want to run. If you just want to run on the most current one, you should still look and see what that is because the default current one changes. We're constantly updating the Python modules on both systems. If you haven't created a virtual environment directory, it's common to put it on your home directory under virtual env, but you can name it whatever you want. I actually put a dot in front of mine just so it's a hidden file. And then you want to cd to that and create this, and you can choose any name you want. You can name it after the project you have. I typically like to put the Python version number in there, just so that I know which version of Python I'm working with. And then this will take a few minutes to actually run. Once your virtual environment is created and you want to use it, you do a source of, again, the path and the name of that. And then the /bin/activate, so that this activates your virtual environment. So anytime you have a Slurm job script that you're going to use it in, you'll want to put a source command, and this drops you right into that environment. If you're still setting it up, then you do your pip installs. Once you activate it, you do your pip installs, and whatever you pip install will only go into that virtual environment and not change your global environment in any way. So that's kind of the basics of creating a virtual environment for Python and why you would want to do it, to kind of keep separate environments for your separate projects. If you're doing this from the command line, is how I've shown it. You can also do this from your Jupyter notebook. And if you do it from a Jupyter notebook, you have to precede everything by an exclamation point. The exclamation point just means that you're doing something in the command line, rather than doing something that the Python notebook should be looking at. Okay, the last thing to cover is migrating Jupyter notebooks to Slurm jobs. Again, Jupyter notebooks are great for developing code because you can literally type something in and hit run and see the result, or see maybe that you did something wrong and correct it right there. So you get kind of the instant feedback and you develop things one section of code at a time. So they're very useful for developing things, but for actually running code in a production environment, they're not so good, because if you ask for 24 hours of time for your Jupyter notebook, for example, through on demand, and you want to run something, then when the job has completed, your resource is still allocated for that 24 hours. So you'll be sitting there idle, using your job will be wasting the resource until you come back and say, oh, my job is done, and I manually kill it off. Slurm job, once your job is done, releases those resources. So it is much more efficient in that way. So we do want to get people to use on demand for development, but then move their jobs to Slurm job scripts once they're ready to run production code. So let's go quickly on how you do that. Here I'm on Beocat. I've logged into on demand on Beocat, and let's just open up a Jupyter notebook here. I'm going to just use the defaults, and launch. This is requesting 1 core, 4 gigs for 24 hours. And here it says, please be patient while it's allocating. Again, Beocat's not running much, so it should just take a moment here. Okay, now it's allocated, so we're going to connect. And I'm just going to do the basic Python 3 kernel. If you do have a virtual environment that you've set up, you can make it so that you can see that under here too. But I'm just going to take the Python 3 default kernel here. And I'm going to do just a basic print statement. And I'm going to run that. So the output said hello from Jupyter Notebook. So now that I've determined that it's running correctly, I'm going to do a save and checkpoint. So my LLT command is showing me that it's saved under untitled. So let me just go back and save as, and let's do we'll call it that and save it. Now, if we look at the file type, the first thing to notice is the IPYNB. That means it's a Jupyter Notebook file. Python NB is notebook. And it's saved in a JSON file. So that's the file type that it's saved in. Now, you can actually convert that manually if you want. So if we do a module load, of Jupyter Lab, that'll get us the commands that we need. See, so the --2 script will change it to a .py file. And so then we can see that it's converted there to a .python file, .py. And it just says it's ASCII text. So we'll look at it. And so this is what we get. These are all preface. So this says it's a Python file. These are all comments because they're prefaced by a £. And you can see these indicators here for input. Those just correspond to the ones right here. So they're kind of junk that gets passed along. But then if you want to run this, you can do it from the command line. We'll load the default Python, and then we'll go Python. And it says hello from Jupyter Notebook, even though we're not on Jupyter Notebook anymore. So if you wanted to run this in a job script now. Let's go ahead and do the other way around. So my job name is Jupyter NB test. I'm loading Python. If I had a virtual environment, I would want to source that. So again, I'm just checking my, so we're going to put that in there, and then we're going to do sbatch and run that. And here's the output. And again, that's an example of how to convert all the way from a Jupyter notebook over to a Python file and then to run it from sbatch. There is an easier way rather than manually converting it like this. You can also, from the on-demand Jupyter file menu, you can download as the .py. So if we go here, so save as will just let us change the name. Save and checkpoint is interesting in that if you ever make a mistake and want to revert back to your saved thing, you can revert to the checkpoint and choose which one you want. We want to go down here to download as Python. And this just downloaded it here to my downloads. And here's now, it's no longer a JSON file. It's on my local machine, and you can see it didn't have to go through the conversion. It converted when it downloaded, but it's the same thing that we got from converting the JSON file over to Python. So those are two different ways of converting the Python notebook file to runnable Python script. And then you just have to submit that as your Slurm job script. So that covers the advanced HPC usage that I wanted to go over today. I hope you found that helpful. And if you have any questions over this, please feel free to contact us.